Hey there, math fans. Welcome to the 1.5 note solving absolute value inequalities. At the top of this, I have a little snapshot that I took from the textbook. And in it probably confuses you if you're to read this out, especially if you've never solved an absolute value inequality. But the one thing I wanted to focus on was their use of the word and here and the word or there. If an absolute value problem is less than the constant side, it's going to be an and problem. Think less than. Okay, so that means it's not eating the absolute value. Um, but if it is eating the absolute value, therefore the absolute value is greater than the constant, think it is think of it as a greater problem. So it's an or problem. And then we'll get into depth and more examples about what it means to be an and problem and an or problem. But basically, you're going to solve these inequalities twice, like you would as if they were an absolute value equation. Um, but if it's an and problem, both those answers have to be true. Like this answer and that answer must be true. And then if it's an or problem, then it's either one of the answers must be true, or both of them can be true. And so it sounds a little bit confusing. So we will talk more about it in depth as I do the examples, but just wanted to kind of preface it at the beginning of these notes. I also wrote here, remember to flip the inequality sign if you ever divide by a negative. That might come up in these notes. If not, it'll come up in a future video for sure. So here on my first example, I have the absolute value of x minus 5 is less than or equal to 3.5. So like I said before, this is a less than the problem. So I'm just going to label it as an and problem. I'll talk about that when I get my final answer. So the first thing you're going to want to do is to just drop the absolute value bars and solve it without changing any signs or inequality signs. So x minus 1.5 is less than or equal to 3.5. So I can simply just add 1.5 to the other side, and I will get x is less than or equal to 3.5 plus 1.5 is 5. And then I'm going to repeat the process, and I'm going to change the signs on one side. What I do is I always change the signs on the constant side. So I'm going to go x minus 1.5 is greater than or equal to negative 3.5. So you'll see that I changed the signs on the constant side, and I also changed the inequality sign. The reason why you do this is basically because of that rule that states if you divide by a negative, you must flip the inequality sign. So if you are flipping the signs on one side, you have to also flip the inequality sign because it's basically the same thing as like dividing by a -1, if you want to think about it like that. Um, and I don't know if you always have to change the constant side, but I do know that I never get it wrong when I change the signs on the constant side. So I just kind of tell my kids to do that. Like, hey, when you're solving it the second time around, change the signs on the constant side. Okay? So I can take the same step I did before, which was add 1.5 to the other side. And I'm going to get x is greater than or equal to negative 3.5 plus 1.5 is negative 2. So here I have my two answers. X is less than or equal to 5, and x is greater than or equal to negative 2. And so this answer, the final answer, will make more sense when you plot it on a number line graph. So if we have negative 2 here and it's greater than or equal to, then I'll put a solid dot here, and it's going to shade to the right. Um, and so it technically shades to the right like that. And then you have less than or equal to 5. So you're going to put a dot where the number 5 would be, and it's a solid dot, and it's going to shade to the left. Now, because this is an and problem, um, both scenarios must be true, right? So where they both overlap is right here in the middle. If you think about it, negative 2 was shading to the right. Positive 5 was shading to the left. So they kind of overlap in that middle area, and you just kind of ignore the areas where they don't overlap because it is an and problem. Okay, so my final answer can be written as what's called a compound inequality. Basically, you're combining two inequalities to make one. And you only ever do that if x is in between two values. So since the shading was in between -2 and 5, I can put an x in between -2 and 5. And the inequality signs have to point to the left. If you were to cover up the x is less than or equal to 5 and just read it as -2 is less than or equal to x, it's eating the x there. That's the same thing as saying x is greater than or equal to -2. And then of course, if you were to cover up this end, it would say x is less than or equal to 5, which is the same thing I wrote there. So usually for and problems, you will not see the final answer written like this because it can be combined to make a compound inequality. So get in the habit of writing your answers like that anytime you see the shading in between two specific values. So in example 2 here, I have an OR problem because it says the absolute value of x plus 7 is greater than or equal to 2. And so sometimes kids think it's an OR problem because it has that OR equals to option, but really it's just the absolute value is greater than the other side. It's greater, think greater, okay? So if it's eating the absolute value side, it's a greater problem. It's an OR problem, okay? So what is that going to mean? Well, let's solve it and find out. So we have x plus 7 is greater than or equal to 2. So you solve it without changing any signs or anything like that. So I can minus 7 to the other side, and I get x is greater than or equal to -5. And then I'm going to solve it again, and I'm going to change the sign on the constant side. So I'm going to say x plus 7, and then I'll have a -2, change the sign on the constant side, and also flip the inequality sign. And here I can just, again, minus 7 to the other side, and I get x is less than or equal to -9. So because this is an OR problem, you'll notice that when we graph this on a number line, our answers are going to go in separate directions. That's pretty common for OR problems, but it's not something that's always going to happen. All right. So here, if I were to draw a number line, -9 is smaller than -5. And so if I graph x is less than or equal to -9, I'll put a solid dot at -9 and shade to the left for the less than direction. And then if x is greater than or equal to -5, I'll put a solid dot at -5 and I'll shade to the right for the greater than direction. Okay, so you can see it going in two directions. So when something's an OR problem, right, that means you can plug in any number that's less than or equal to -9 and it'll make a true statement, or you can plug in any number that's greater than or equal to -5 and that'll make a true statement. If you plugged in any number in between -9 and -5, that would make a false statement, okay? So that's basically what that means. And so OR problems are never written as compound inequalities. They are always written as OR statements. So you have x is less than or equal to 9 or x is greater than or equal to -5. That would be your final answer. You always want to put the smaller statement or the less than statement on the left and the greater than statement on the right. So in example 3 here, I have some stuff going on outside the absolute value bars. So before I determine if this is an and or an or problem, you want to get rid of whatever's on the outside of the absolute value bars to the other side first. So always start by adding or subtracting. So I'm going to look at this +1 and minus it to the other side. And so here I have 4 times the absolute value of 2x minus 5 is now greater than 20. And so instead of distributing the 4, since there's a constant on the other side, what you'll want to do is actually divide that out. You don't necessarily have to, but I always recommend that kids do that. In my opinion, it makes things easier, especially if that 4 were a negative, because then it would change things up a lot if it were a negative. Um, so, yeah, if you can divide it out to the other side, then I recommend that you do so. So 20 divided by 4 is 5, and that's just going to bring down the absolute value of 2x minus 5 here, and then it's greater than 5. So because it is eating the absolute value side, that means the absolute value side is greater than the other side. So that makes this an OR problem. So I'm going to solve this as 2x minus 5 is greater than 5. So I can simply add 5 to the other side. And so we have 2x is greater than 10 and divide by 2 and we'll get x is greater than 5. So that's my first answer. So I'm going to change the signs on the non-absolute value side. So the non-absolute value side will be changing the 5 to a negative 5. And then I'm going to flip the inequality sign. So now it's eating that side. And so it's going to say 2x minus 5 on this side. So I'm going to follow basically the same steps. I can add 5 to the other side. And I'll get 2x is less than 0. A lot of times when kids get 0 during the process of their answer, they think they either messed up or the answer is going to be no solution or something like that. But yeah, sometimes you can just get 0. 0 is a regular number after all. It's just because you don't have answers equaling 0, I guess, all that often, kids think something must be fishy about it. So if you were to officially show all your work, I would divide 2 to the other side. Granted, once you get to this point, you could just kind of conclude that if 2x is less than 0, then x is less than 0. So I have my two answers as x is greater than 5 and x is less than 0. So if I were to plot that on a number line, I'd use an open circle at 0 and an open circle at 5 because those inequality signs were not underlined. There's no or equals to option. And so x is less than 0 shades to the left, and x is greater than 5 shades to the right. So it's going in two separate directions. That's basically what's happening in this OR problem. You can plug in any number less than 0, like -1, -2, whatever, or I could plug in any number greater than 5, like 6, 7, 8, 9, 10, whatever, and it'll make a true statement. So to write your final answer, this is an OR statement, right? So you're going to put the leftmost statement or the one going left first. So x is less than 0 or x is greater than 5, and that's my final answer. So in my final example here, I had a bit of a typo and I put the wrong sign. But you'll always want to start by looking to get rid of anything outside the absolute value bars first. So I can add 7 to the other side. And so instead of distributing that 3, I can just as easily divide it over to the other side. And so then I'll get the absolute value of x plus 1 is less than or equal to 2. So the absolute value bars are on the less than side, making this a less than problem. So I have an and problem right here. And so now we're good to go solving this inequality. I'm going to do x plus 1 is less than or equal to 2. And then I'm also going to do x plus 1 is greater than or equal to -2. So this is a pretty simple inequality to solve. I can minus 1 to each end, and I'll get x is less than or equal to +1. And I'll also get x is greater than or equal to -3. What you'll want to do now is graph it on the number line and see how that and scenario is going to affect your final answer. So here I'd have -3 and +1 on my number line. They're both getting solid dots because of the or equal to option. So the first one says x is less than or equal to -1, so that's going to shade to the left. X is greater than or equal to -3 will shade to the right. And so since it's an and problem, the overlap is where they are true, because it needs to be true for x is less than or equal to 1 and x is greater than or equal to -3. So in other words, x is in between -3 and 1, so you'd write your final answer like this as a compound inequality. And with that, that's going to wrap up these notes. I thank you for watching. I hope you learned something, and goodbye.